Welcome to the lecture. You may kindly recall that in the last lecture we had described the setup of multiple linear regression model like y is equal to x beta plus epsilon. And we considered here that that y is linearly related to x1, x2, xk through the regression coefficient beta 1, beta 2, beta k. Before we try to estimate the model parameters, a natural question comes that how do we decide that the relationship between y and x1, x2, xk is linear or not. So, we take the help of a simple linear regression model in which, if you recall, I had made a scatter diagram like this, where I had taken x and y independent and dependent variable, and we had made a scatter diagram of the given observation, and in case it is looking like this, we can say that there is a linear trend, and possibly the relationship between x and y is going to be linear. But now if you try to see in this case, we want to see the joint effect of x1, x2, xk on y is linearly related or not. So, in the earlier case of simple linear regression model, we could work only with a two-dimensional figure. But in this case, there is going to be a high dimensional picture, and up to third degree possibly I can make a three-dimensional plot, but beyond the third degree I cannot make a plot. So, in this case we try to take the help of so called multiple scatter plot. Multiple scatter plots are not difficult to obtain, they are readily available in any software, and in the case of multiple scatter diagram, they are essentially trying to plot the scatter diagram among all the variables pairwise. So, for example, if I say if I have here a model something like y equal to x1 beta 1 plus x2 beta 2 plus say epsilon, where I have got only two independent variable. In this case, the multiple scatter plot will look like this. This will be a sort of 3 by 3 diagram in which we try to plot y x1 x2 here and y x1 x2 here. So, what really happened that in this section this will be a picture between y and y. So, there is no question of considering this graphic. Similarly, here in this section the graphic is going to be between x1 and x1, which has no meaning, and similarly here the graphic is going to be between x2 and x2, which has no meaning. But here this will give us a scatter diagram between y and x1. Y is coming from here and x1 is coming from here, and here there will be a scatter diagram between y and say x2. So, x2 will be coming from here and y will be coming from here. So, we try to look on this individual scatter diagram, and then we try to take a decision whether the joint relationship between y and x1 and x2 is going to be linear or not. Well, in a simple interpretation, if I say if the relationship between y and x1 is linear, y and x2 is linear, then we expect that the relationship between y and x1 and x2 will also be linear. But there can be some more complicated situation. So, we will try to take up some numerical example later on, and we will try to demonstrate that how do we take a decision in such situation. So, one thing we have to notice that this section will give us a scatter diagram between x1 and x2. What does this mean? So, I would try to demonstrate it it here, that how does it help us actually. If you remember, we had made an assumption that rank of X matrix is going to be K, that is the same as the number of independent variables or number of explanatory variables. So, this implies that all x1, x2, xk, they are going to be independent. They are going to be rather linearly independent. So, we need to ensure before we go for any linear regression analysis that whether these assumptions are verified or not. So, this multiple diagram will help us in diagnosing the issue that for example, in this case x1 and x2 are independent or not. So, in case if we see as a sort of linear trend or say any other type of relationship, that would indicate that x1 and x2 are not independent, right. So, and in this multiple scatter diagram, this is a symmetric diagram. This is symmetric. Symmetric in the sense that whatever is the picture here, the same picture will be here, and the same picture will be here, and the same picture will be here. So, this is how, using the concept and idea of multiple scatter diagram, we decide whether the relationship between y and all x1, x2, xk is linear or not. Right. Now, we come on another important aspect, and we try to estimate the model parameter. So, again, because for the sake of understanding, we are going to consider here a model y equal to x beta plus epsilon, where y is a n cross 1 vector of observations on steady variable, x is a n cross k matrix of n observation on each of the k independent variable, and beta is a k cross 1 vector of regression coefficient beta 1, beta 2, beta k, and epsilon is a n cross 1 vector of random error components. And we assume that epsilon is following a normal distribution with mean vector 0 and covariance matrix sigma square I, right. So, our model parameters in this case are beta vector, or it is equivalent to saying that beta 1, beta 2, beta k and sigma square. So, there are altogether k plus 1 model parameters that need to be estimated to describe the model completely. Right. So, in order to estimate these model parameters, we have two options. First thing is this: I can use the principle of least squares, and second is method of maximum likelihood. So, just like in the case of simple linear regression model, we will try to use the principle of least square as well as maximum likelihood estimation in the case of multiple linear regression model also. So, first we are going to talk about the principle of least squares, right. If you recall, in case of simple linear regression model, the model was y equal to beta 0 plus beta 1 x plus epsilon, and we had minimized the sum of squares due to random error summation I goes from 1 to n epsilon I square. And our objective was that we wanted to find out the value of beta 0 and beta 1 by minimizing the sum of square due to random errors. Now, in this case, if you try to see, this is not a two-dimensional problem, but there are parameters beta 1, beta 2, beta k and sigma square. So, obviously, first we will try to concentrate on the estimation of beta 1, beta 2, beta k, and sigma square will be estimated later on separately. So, if you try to see, we are working here in a k dimensional Euclidean space. space. And let us try to define, suppose capital B is the set of all possible vectors in this k dimensional Euclidean space. So, now our objective is that we want to find out the value of parameter vector beta such that the sum of squares of random error is minimized over this entire space, right. So, now I can define my objective. My objective is to find, say, beta hat, which is actually beta 1 hat, beta 2 hat, say this beta k hat vector from B that minimizes summation I goes from 1 to n epsilon I square, right. Okay. So, now let us try to do it. So, he will define here a function, say S beta, which is something like summation I goes from 1 to n epsilon I square, and this I can write down as, say, here epsilon transpose epsilon, where epsilon is a n cross 1 vector, right. Okay. So, now the same thing can be written as epsilon can be y minus x beta transpose y minus x beta. Okay. And if I try to open this, then we get here y transpose y minus twice of beta transpose x transpose y plus beta transpose x beta, right. And we assume that this S beta is a real valued convex differentiable function, so that the minimum will always exist, right. Okay. In order to find out the minima, we are going to use here a simple result. So, before doing anything, let me state this result. Suppose z is a random variable of, say, order m cross 1. So, this is a m cross 1 vector. Now, in case if I try to consider here a quadratic form, something like z transpose a z, right, then partial derivative of z transpose a z with respect to this z is a plus a transpose times here z, and this becomes twice of a z if a is symmetric. So, we are going to actually differentiate the function S beta, and during this process we are going to use this result, right. So, now if we try to say this differentiate S beta, partially differentiate S beta with respect to beta, we get here twice of x transpose x beta minus twice of x transpose y, right. So, from here I can obtain the normal equation by partial derivative of S beta with respect to beta equal to 0, right. So, we have this equation here as, say, x transpose x beta minus x transpose y is equal to 0. So, what we try to do here, that we pre-multiply by x transpose x whole inverse. So, we get here x transpose x whole inverse x transpose x beta is equal to x transpose x whole inverse x transpose y. So, this finally gives us that beta hat is equal to x transpose x whole inverse x transpose y, right. Now, we have to also ensure that this value of beta hat really minimize the sum of squares due to random error, which is S beta. So, in order to do so, we try to find out the second order partial derivative with respect to beta, and this comes out to be here twice of x transpose x, right. So, this matrix is at least non-negative definite, right. And so, this ensures that beta hat minimizes S beta, right. And then this now beta hat equal to x transpose x whole inverse x transpose y, this is called as ordinary least squares estimator of beta. One thing we need to note here is the following, that here we are going to use the term x transpose x whole inverse. How do we ensure that whether this inverse will always exist or not? So, if you recall, we had made an assumption that rank of X matrix is equal to here K. This was a full column rank matrix. So, then X transpose X is positive definite, and so X transpose X whole inverse always exists. So, you can see here that whatever assumptions we had made, they have some utility. They are going to be used in the mathematical derivation of the results, and they will have some practical issues also that we will try to address later on. So, now what you have to always keep in mind this result, that this ordinary least square estimator of beta. And remember one thing, here beta hat is not a scalar, beta hat is a vector here, something like this. If you try to see here, I can write this beta hat is actually beta 1 hat, beta 2 hat and beta k hat. And so, whatever you are going to get after solving this equation, you will get a vector, and the individual values of that vector, they are going to give us the individual estimates of the elements of beta vector, right. So, once I have obtained beta hat, then I can obtain the fitted model. The definition of the fitted model carries over from the definition that we described during the simple linear regression model, that we try to estimate the model parameters and we substitute the model parameters in place of the parameters, and the model that we obtain, that is called as a fitted model. So, in this case, if you see, we had a model y equal to x beta plus epsilon, and now we are going to replace beta by beta hat. So, this becomes our fitted model, right. So, this can further be written as something like this, x transpose y. So, here we will try to denote it by here h y, and where h is x transpose x whole inverse x transpose, right. This matrix has a particular name, and this is called as hat matrix, and you will see later on that this hat matrix plays an important role in the linear regression analysis, and H matrix has some nice properties also. But before that, I can also define another quantity, say H bar, which is I minus H. I is an identity matrix. Okay. So, both this H and H bar, they have certain properties, right. First important property is that H and H bar both are symmetric matrices, right. Second important property is that H and H bar both are idempotent So, that means h into h is equal to h, as well as h bar into h bar is equal to h bar. Third important properties that we are going to use is the trace of h. What is a trace? Trace is the sum of the diagonal elements of a matrix, right. So, if you try to find out the sum of diagonals of H matrix, then this is trace of x, x transpose x whole inverse x transpose, and we have a popular result in the matrix theory that trace of AB is equal to trace of BA, where A and B are the two matrices where and their product is well defined. So, I can write down this thing here as a trace of, say here, x transpose x whole inverse x transpose x, and then this become trace of here I k, and I k is an identity matrix of order k by k. So, this trace is actually here k, right. Similarly, if you try to find out the trace of h bar, this becomes here trace of say I minus here h. So, trace of identity matrix of order n by n minus trace of here h, and this comes out to be n minus k. So, these are some results that we will be using later on. Okay. Okay. So, now after this let us try to describe how do we define the fitted values. You may recall that in the case of a simple linear regression model, we had obtained the fitted values by providing the values of independent variables to the fitted model, right. Similarly, exactly on the same lines, I can define the fitted value here as for a given x, the fitted values are denoted by y hat, and they are defined as y x beta hat, right. Okay. Next quantity we are going to define about the residuals. If you try to recall, during simple linear regression model, we had defined the residuals as the difference between observed and fitted values of steady variable. Exactly on the same lines, I can define it here as a epsilon hat, which is y difference y hat. And so, more logically, I can write it down here as say y minus y hat. So, now we have obtained y hat here is x beta hat, and beta hat we had obtained as say here y minus x transpose x whole inverse x transpose y. So, I can write down here y minus h y, and so I can write down here I minus h times here y. So, this is equal to here h bar y. So, this is a very convenient notation for us to use to present the epsilon hat, which is our residuals. Okay. So, now we stop here, and in the next lecture we will try to investigate the properties of ordinary least square estimator of beta. Till then, goodbye.